Okay, welcome back everyone. So the first speaker of the afternoon will be Luiz Agostinho Ferreira from Instituto de Física de San Carlos, who is going to talk about the hidden symmetries of Young mills in 3+1 dimensions.
Thank you. Well, first of all, I would like to thank the organizers, Marina, Horacio, Javier, and all others for this very nice meeting. Put together different kind of people, And second, it's a pleasure for me to be here because I was a faculty member of IFT for 20 years. And my office was in the first floor of this old house you see there. And, sorry? Yeah. There, yeah, there. And so it's a great pleasure to be here, okay? So, as he said, I'm talking about the hidden symmetries of Young-Mills theory in 3+1 dimensions. That's a work with my student, Henrique Malavasi, PhD student. And the contents of the talk is in this paper that appeared on Monday, 3 days ago, on the archive, okay, with the same title. When, with half an hour, you say that. Give me this sign, okay? Okay, let me tell you the outlook of the talk, that what I'm going to do, the first part of the talk, is to present two novel symmetries of Young-Mills theory in 3+1 dimensions, right? And what I'm going to talk here applies to QCD, to the Weber-Xelan model, to the standard model of interactions, right? The Young-Mills theory I'm talking about here is not supersymmetric, okay? So the first one, it's an infinite set of global transformations generated by the conserved quantities, which are the electric and magnetic charge and their higher modes, okay? And these are generated by the Poisson bracket. It's as simple as that, okay? You take the charge, write it in terms of the canonical variables, and calculate, if you want to calculate the transformation of a given function of the canonical variables, just calculate the Poisson bracket. That's it, okay? As simple as that. And the second one, mathematically, is a bit more involved because these are the symmetries of the integral Young-Mills equation, which I'm going to explain you in a moment. And this is an infinite dimensional group of symmetries, and the elements of the groups are anomalies of connections on loop space, okay? So, in fact, we can prove quite easily it's a group, but the structure of this group is quite complicated. We don't understand yet. We don't know even if it's a Lie group. It might be interesting that if it's not a Lie group, because you can circumvent Coleman-Mandula without supersymmetry, okay? And those symmetries lead to a complete integrability structure on the space of electric and magnetic charge. You have an infinite number of conserved charges, and they are in involution, okay? I'll show you the R matrix and the fundamental Poisson bracket relation and Skilianin algebra that leads to this involution, right? The R matrix is very simple, as you see. But the point is, what I want to call your attention, that we are used to integrability where the conserved charges are the energy, momentum, and the higher modes of the energy or momentum. So this integrability leads, for instance, to the factorization of the S matrix. You cannot have that in Young-Mills theory because you know there are part productions. The S matrix is far from being factorizable, okay? So the charges, they are internal charges, not space-time charges. They are the non-abelian electric and magnetic charge and the higher modes of it, even though all of them commute with the Hamiltonian, okay, as I will show. And the technique that allowed all these is to work with the flat connections on generalized loop space, okay? And the electromagnetic charges are really gauge invariant. They are truly gauge invariant. In fact, these charges, we got it about 12 years ago, and they solved a long-standing problem in classical Young-Mills theory. That's the definition of electromagnetic charge. If you go to the original papers of Young-Mills, they already call the attention to this, that those charges are not really gauge invariant. They are gauge invariant if you impose gauge transformation that goes to the identity at infinity. But this one, no, they are invariant under small and large gauge transformations, right? And the interesting thing, being gauge invariant in QCD, they are color singlets. They are scalars under the color group, okay? So they may not be confined, and the hadrons, I mean, the baryons and mesons, could well carry these charges. The challenge is how to inspect that, okay? I'll tell more about this. We have done this in 1+1 dimension, and the hadrons do carry these charges, but not the quarks, okay? So it's a charge that if they come to appear on the hadrons, they don't come from the constituents, they come from the interaction, so the gluons, okay? You don't take the charge of the quark and add up and get the charge of the proton, no. The quarks very probably don't carry this charge. The charge is carried by the interaction, okay? Okay, but before I go to the proper contents of the talk, I want to fix the notation, just to make sure what I want to upload to higher dimensions, right? So take this, I know all of you know very well, is the sine-Gordon model. You have the Lax pair, these are the two components of the flat connection. Theta is the sine-Gordon field, lambda is a complex parameter, the famous spectral parameter, right? And if you calculate the curvature of this connection, it's proportional to the sine-Gordon equation times sigma 3, okay? So whenever the sine-Gordon equation of motion holds true, this connection is flat, okay? And that's the magic, because first of all, F mu nu equals 0 has this symmetry, which is the gauge symmetry, and that's the hidden symmetry. It's a symmetry of this representation of the equations of motion in terms of the Lax pair, but it's not a symmetry of the equations of motion, of the Lagrangian. That's why they're called hidden symmetries, okay? I'm going to show you the equivalent of this for the Young-Mills theory, okay? And this thing lives on a loop algebra because of this spectral parameter. If you switch on the center term, you get the Kac-Mood algebra, and so on. But the thing, I mean, the most important thing in this talk is this concept of path independence. And this has to do with the following. If the connection is flat, then the holonomy of this connection, which is the Wilson line, is path independent, okay? That's, you can use the Stokes theorems, whatever you want to show that. And then take space X and T, they are one-dimensional, and take two paths connecting the same 2 points, okay? So since it's independent, the holonomy in this path is equal to that one, in that other path. And then if you impose boundary conditions like these, the holonomy here is the inverse of the holonomy there, and then you have isospectral evolution of the space holonomy at t equals 0 and t equals t. So the eigenvalues of this holonomy are constant in time. Since this depends upon that spectral parameter lambda, you can expand in powers of lambda, you get an infinite number of conserved quantities. So these are the conserved quantities of sine-Gordon model. And that's classical integrability as the most basic level, okay? Good. So if there are any questions, please interrupt me whenever you want. So let's go to the main ideas of the talk, okay? First of all, you have Nutter symmetries versus hidden symmetries. Nutter symmetries are very important, of course, okay? But all these developments, especially in integral 1+1 field theory, didn't come from Nutter's theorem. They come from hidden symmetries. Because the Nutter's theorem, they leave the Lagrangian invariant, the Hamiltonian invariant, and so, but the hidden symmetries, no. They take a vacuum solution, bring to a non-trivial solution. So, that's why we're going more interested in the hidden symmetries. So, as I said, in 1+1, you have this structure, which is the flat connection, and the holonomy, which is path independent. The path independence is equivalent to conservation loss. Okay? So, how do you go to higher dimensions? Okay? The idea is to use loop space. What you do is this. You take this loop space with a space of functions from the sphere, d-1 dimensional, to the space-time M, such that the north pole of the sphere goes to a fixed point on the space-time. That's what's called a based loop space, okay? And the XR is the base point. Now, if you take a volume in space-time omega, you can scan it with closed surface, a d-1 dimensional surface, right? So the image of this mapping is a closed surface in space-time. So this closed d-1 dimensional surface are points in that space, okay? So if you scan the volume with closed surface, the volume becomes a path in that space, okay? That's the idea. For instance, take a two-dimensional surface. Take the reference point at the border and scan it with loops. So this becomes a path in loop space, okay? That's crucial because it's like being one-dimensional, right? That's how you connect with 1+1. You wrap the space in a path, okay? That's the basic idea. So, and then what you do? You look for a flat connection on the loop space. And the holonomy of that connection is going to be path independent. And then you have conservation loss if you impose proper boundary conditions, okay? So the eigenvalues of this holonomy are going to be constants of motion, like in the Sine-Gordon model, okay? So that's the approach we proposed about 30 years ago, okay, in 97, with Orlando Álvares and Joaquim Sanchez-Guilhem. But even though the idea is nice, you know, it's quite easy to have nice ideas. The problem is how to implement them, okay? That's the problem, okay? So this idea has two problems. The first one, the connection is flat in loop space and it's local in loop space. This equation here is local in loop space, but not in space-time. If you want this to be equivalent to the equations of motion of local field theory, you have problems, right? Because you need something which is local in space-time to impose a local condition in loop space, and this is highly non-local in space-time. That's a problem. The second problem is this. If you change the scanning of the surface, you change the path in loop space, but the physical surface is the same. So you have an infinite number of paths in loop space corresponding to the same physical surface, okay? That's called the reparametrization invariance problem, okay? We have many applications, even with these problems, we managed to have several applications, but I will not talk about them here. And the good news is that the theory that's most important for us, high-energy physicists, is that gauge theories fit neatly in this scheme, okay? I mean, it's surprising. And why it does? Think of Maxwell theory, right? the simplest gauge theory we know of. So the dynamics of classical Maxwell theory can be described by Maxwell equations, which are local in space-time. But the electrodynamics was developed first with integral equations, like the Gauss law, the Faraday law, and all these things, okay? But in these laws, for instance, the Gauss law, if you take a volume which is totally spatial, the charge inside equals to the flux of the electric field, right? If it has a time component, you get Faraday law, okay, and so on. So Maxwell theory can be described locally in space-time with Maxwell equations, but it can be described locally in loop space with the integral equations. So it's a special theory, guys. The dynamics of it, you can phrase it locally in space-time or in loop space. That's crucial. And it's amazing that what fits in this scheme that we had proposed 30 years ago is exactly gauge theories, okay? So then we need integral equations. The integral equations for Maxwell theory were known for a long time. But for Young-Mills, no, okay? Then what we want, since it's non-abelian, the volume integral has to be ordered and the surface volume has, the surface integral has to be ordered too. So we want equations like this, okay, to be true on any volume in space-time, in four-dimensional space-time. We want equations like that, which apply to any volume in space-time. And the magic of this equation is this. If you change the volume, but don't change the border, this side changes, but the other doesn't. But I impose this to be true in any volume, so this has to be equal to that, but then it is equal to that one. So it means that the right-hand side of this equation is independent of the volume, as long as you keep the border fixed, okay? To change the volume without changing the border, you have to go to 4 dimensions. Think of a drum, okay? You have it fixed on the border, and you can oscillate it. So you change the surface, but you don't change the border, right? So you go 1 dimension higher, and you have what we need. So then it means that this holonomy is path independent already. You see? I don't even need the flat connection, but the flat connection follows from this path independence, okay? You get it for free. Yes. No, I'll show you. I'll show you in a moment. This A is a connection in loop space, built from the Young-Mills fields. Just a second. So the magic is local Young-Mills differential equations imply integral equations which are local in loop space, okay? So the flatness condition in loop space are equivalent to local in space-time, and that's the thing we did 12 years ago on these 2 papers with my PhD student, Lucchini. Well, he was a PhD, now he's a professor in thing. Okay. Okay, good. Now, the technique. How do you do these things? How do you implement, you see? The thing is non-abelian Stokes theorems. Maybe you are used to the usual non-abelian Stokes theorems for 1-form connection. We need a non-abelian Stokes theorem for a 2-form connection, okay? So what we do is this. I take a surface and I scan it with loops labeled by tau, and the loops are parametrized by sigma, okay? I will use 2 fields. First is a 1-form connection in space-time, and I build it, the Wilson line of this connection. This will be an auxiliary connection. And then I take a rank 2 tensor in space-time and construct this, which is a 1-form connection in loop space. This integral is over the loop parameterized by sigma. It's a closed loop. Sigma I and sigma f are the initial and final points, which are the same, okay? So the holonomy equation is this one. So the holonomy, you can write it as a surface order integral, of this B mu nu conjugate by the Wilson line, okay? But the theorem follows like this. Now take this surface as a closed surface, right? And then you take XR, which is a point in space-time, and blows the two-dimensional surface, scanning a volume now, and parameterized by zeta. And you define, what you do is the following. Here's a trick point. You calculate from here the variation of V when you vary the surface. So the trick point is you don't vary V here, you vary V on the equation, and you get an equation for the variation of V, and you integrate it. And you end up with the V minus 1, delta V minus 1 is an integral in tau, which is this one. So you get a differential equation for V. And now I look for the variation of the surface as this is scanning, right? So then I can calculate V on a closed surface, which is the border of this volume, either by integrating directly on the border or by integrating through the volume, right? And since they are built from the same thing, they have to be equal. That's the non-abelian-Stokes theorem. Okay. Now, the local Young-Mills equation are the following. You take, the integral equations. You take the local, yeah. Sorry? I'm going to say now. Just now. B mu nu, that theorem is a mathematical identity. There are no equations of motion there. It's an identity. One side is equal to the other, independent of B mu nu and A mu. Yes. Volume ordering. Yes, that's the scanning. You choose a scanning. So you scan the volume with closed surface. You can change that scanning, of course, but choose one. And then you scan every closed surface with loops. And the loops are parameterized by sigma. So I have to frame the volume in this scanning. But I can change the scanning. And at the end of the day, everything will be independent of this choice of scanning. So take the local Young-Mills equation. That's the Bianchi identity, and that's the Euler-Lagrange that comes from the Young-Mills action. And this is the Hodge dual of the matter current. I'm using here leptons and quarks and the Higgs field, for instance, right? That's the matter current, okay? So what you do, you make a linear combination of these two equations, and this comes your B mu nu, is alpha times F mu nu, beta times F mu nu tilde, right? Times the coupling constant, the gauge coupling constant, times I. So these two equations imply that B mu nu satisfies this equation. What you do? You plug it in the Stokes theorem, and you get this equation, okay? Remember that there was the covariant stereo derivative of B appearing there. It's going to be replaced by the dual of the matter current. And here is the matter charge, because that's what's in there, because that's the volume integral, that's the charge inside, and here's the gluon charge, okay? So that's the integral Young-Mills equation, okay? You see, if you expand both sides in powers of these three parameters, alpha and beta, you get an infinite number of integral equations. Okay. So the conserved charge. The conserved charge is this. You take the space R3 and you integrate the volume. The volume is R3 now. The border is the surface at infinite. And you impose these boundary conditions are enough to get the isospectral evolution of that operator. So this operator times t is that same operator's time t conjugate by u, which is of the same form as that thing, in fact. Okay. So the boundary conditions are quite reasonable, you see. So then the charges are the eigenvalues of this operator or traces of powers of it, okay? Since they depend on two arbitrary parameters, you have an infinite number of charges, okay? That's it. And the charges are gauge invariant. They are independent of the reference point. I don't have time to prove it, but I can show you how, why it is. And it's independent of parameterization. The independence of parameterization now is obvious because this thing is path independent. And the path, you can change the path either by changing the volume or by changing the scanning. Both things change the path in loop space. So this is guaranteed already from the integral equation. An important point is this: everything in our equations are conjugated by the Wilson line. So if you make a gauge transformation, the F and J transform like this. One point, look, the current is transformed under the adjoint, but that's because I took the matter currents that transform under any representation of the gauge group, but I contract with the generators of the gauge group. So it's an element of the Lie algebra, okay? So it transforms under the adjoint because it's conjugate is a Lie algebra element. So this means that the conjugated quantities by the Wilson line, they are global. They have a global symmetry, but not a local one. Because the local gauge symmetry disappears. Okay? They disappear. And GR is the value of G at the reference point. So in all my equations, I have global symmetry, gauge global symmetry. The local gauge symmetry disappeared. So in some sense, these integral equations do what Miguel and Makaenko tried to do with the Miguel and Makaenko equations, right? To write the dynamics of Young-Mills in terms of gauge invariant quantities. So the Wilson line is not enough to do it. You have to work with these funny things, fluxes and these things. So you can call this integral equation improved Migdal-Makaenko equations, okay? Now, I'm running out of time, but let me show you a closer look now at the conserved quantities. There are some things here which are important. If you look at the currents, there are two objects which are very important. They are fluxes. This is the non-abelian electric field, the non-abelian magnetic field conjugated by the Wilson line. And then there is an area element. So they are defined on a loop, okay? And you have an area band, an infinitesimal area band attached to it. And it can be attached in two directions, either parallel to the surface or perpendicular to the surface. That's the tau and zeta thing, right? So these are the flux. And the charge operator is the holonomy of that connection, which involves this, what I call the current spatial, because it's integrated only over space. So it has this form. But the important thing is this. This thing here comes from the matter currents, the density of so this is the electric charge of the matter fields, okay? And this thing, which appears there, is the electric current, the electric charge density of the gluons, okay? And this is the magnetic, the density of charge of the gluons, okay? And if you, as I said, you can expand the integral equation in powers of alpha and beta. If you take first order in alpha, you get this equation. So the integral of the magnetic charge over the whole space is the flux of the magnetic field conjugated by the Wilson line. Everything here has global symmetries, not local ones. The local ones will have been wrapped up. And here is the electric part of it. So the matter is easy because it's what, but this is new. This I never saw in the literature, that the gluons carry this charge density, you see. Okay. So now, as I said, the symmetries are generated from the Poisson bracket, so I need a symplectic structure. Okay. So the symplectic structure is the simplest one you can think of. Go to chapter 3 of Fadeev's-Levinov book and get it from there. That's the symplectic structure. That's the Young-Mills Lagrangian, okay? And you have the Poisson bracket between the space component of A and the conjugate momentum is the electric field, right? And here is for the matter fields. So the Hamiltonian has this form. CA are the Gauss constraints, right? And A0 becomes a Lagrange multiplier, right? And here the constraint involves the matter and gauge part, okay, and that's it. So, the transformations are these. You take the conserved currents and calculate the Poisson bracket with any quantity that are functional of the canonical variables. And that's the transformation, is a global transformation of any quantity. Okay, it's generated by the charge. Okay, now, why is it symmetry? It's a symmetry because it leaves the Hamiltonian invariant. And this symbol means it's zero, weakly zero, when the constraint holds true. Okay? So these are the, and the funny thing is that the charge commute with every part of the Hamiltonian. There is no term from here canceling terms from there, no. Each one is invariant under the transformations, okay? Sorry? No, no, no. I'll show you how the fields transform in a moment. I'll show you how the local fields transform, like the Wilson line transforms and like the flux transform. Okay. So the algebra of charge. Okay. I want to know what sort of algebra they satisfy. And here comes a big surprise. I mean, we didn't expect that. And if I were sitting there, I wouldn't believe what I'm saying, right? I wouldn't buy it. And you should not buy, okay? It's too good to be true. So, again, the charge operator is the holonomy of this connection. And the thing, here I'm taking this connection, calculate on R3. No, not R3. On a surface, on a spatial surface. It has no time component. Because you know, the fundamental Poisson bracket relation for the integral models involves only the space component of the Lax connection, right? Here's the same. I take these defined on a closed surface, but it's space, no time component. The thing is, if you take two of these connections in different surfaces, zeta1, zeta2, okay, with different parameters, alpha 1, beta 1, so on, you get the fundamental Poisson relation, but anomalous. They have this anomalous term whenever alpha 1 and alpha 2 are not equal. And the R matrix guy, this R matrix is the simplest R matrix you can think of for a Lie group G, okay? Is the rational R matrix for the current algebra for the principal Carroll model. That's it, okay? And this thing here, the sigma constraint, it vanishes by imposing the constraint, but that one doesn't, okay? So it's really an anomalous fundamental Poisson bracket relation. But this term will not spoil the involution of the charge. So now, once you have the Poisson bracket between the connection, you can calculate the Poisson bracket between the charge operators. And you get the Skilianin relation, which is this, okay, with the same R matrix, but with some other quantities here that derive from those ones, okay, this thing. But when you impose the constraint and boundary conditions, the boundary conditions are those ones I showed you for the conservation of the charge, but there are some other boundary conditions for the invariance under reparameterization, which are quite subtle. I don't have time to show you. I'll be happy to explain what it is in the questions or even after the talk, because that's a very interesting thing. But I don't have time to do it. So the charges are in involution, okay? They are weakly in involution. Whenever the constraints hold true and the boundary conditions apply, they commute among themselves. So it's an infinite number of charges that commute among themselves, okay? But the transformations don't commute. The transformation generated the charge don't commute because when you commute on any quantity x, you get the Poisson bracket of this x with this quantity. This is epsilon. I won't show you the form of it, but it vanishes when the constraints hold true. I cannot impose the constraint inside the Poisson bracket, so this commutator is not zero. But this quantity here commutes with the Hamiltonian, so it's a conserved quantity. It's a new conserved quantity, right? But it vanishes on the constrained phase space. So you take all these conserved quantities I have, calculate the transformation, and there is a guy there, which is like a central term, right, that prohibits of the transformations to commute, even though the charges do commute, right? But when you try to look at the physical value of that charge, it vanishes, because you have to go to the constrained phase space. So we still have to explore more this, okay? But that's a subtle point. Now, let's go for the transformation of fields and Wilson lines and so on, okay? Let's start with the matter fields. So, take any leptons, quarks, or Higgs fields. Psi stands for any one of them. So it transforms under a gauge, that's a gauge transformation, a usual gauge transformation, local one, okay? And transforms some under representation R, okay? Under this global transformation, it transforms like this. The infinitesimal variation of it is this Poisson bracket. That's the constant global parameter. And here it rotates under that representation the same way as there, you see. But it picks a phase. And this phase is independent of the component of the moot plate. Okay? So all components of the moot plate get the same phase, which is this thing. So that's the charge operator to the power n, because I'm calculating the transformation generated by the Qn, right? And S is a volume order operator. Okay, it's integrated over the volume, which depends on all fields of the theory. Matter fields, gauge fields, and so on. They have the same nature as Q, right? But they are not the Qs. And then you have a contraction between the generates of the Lie algebra, TATA. Okay, that's it. Since this phase doesn't depend upon R, any gauge invariant monomial of the fields is invariant under this transformation. But as you asked, it's not a gauge transformation. It's a global transformation that a piece of it is like a, if you cut that thing and leave the epsilon there, that's the gauge transformation. But it picks this non-integrable phase. Okay. No, this guy is not gauge invariant. If there are gauge invariant operators that transforms under that, yes, you can have. I'll show you, for instance, terms in the current, in our matter currents and so on, they can transform. Well, for instance, if you take monomials of psi, like psi bar psi, that's invariant under the global transformations. But you can think more other things which are not, and they are not invariant. They may not be invariant. You may have to use boundary conditions to get the invariance, but in principle they are not. Oh, another thing is I want to call the attention is this. The calculations here are quite involved. I'm not showing you this, but they are plugged with surface terms. The surface terms are crucial for everything here. Okay, surface terms are very important. Now, the fluxes. I have in the paper the transformation of the gauge fields, but the gauge fields are not primary fields. Okay, it's better. I'll show you how the flux. First, the flux. How the flux transform. So if you take those two fluxes I showed you, the transformations are quite simple. The magnetic flux is invariant under any transformation, but the electric flux is not. It picks up a phase similar to the matter fields, but this S is different from the other one, but it has the same nature. It's the same nature, and this is the charge operator to the power n, and it rotates under the adjoint, because this guy transforms under the adjoint. Under a gauge transformation, local one, it transforms globally under the adjoint. So here is the transformation under the adjoint. If this thing was constant, then it would be a gauge transformation, right? But this phase depends upon all fields. Now, the Wilson lines. The Wilson lines, you have to take some, you can calculate for any Wilson line, but things get complicated very easily. So, I'll show you the ones that have the simplest transformations. As I said, I have this scanning. Take a volume, and you scan it with closed surface labeled by zeta, and you scan each surface with loops labeled by tau, and each loop is parameterized by sigma. So in R3, I'll have my Wilson line restrict to R3, okay? I have one-to-one correspondence between the points of R3 and these three parameters, right? So I introduce three Wilson lines. One in the direction of sigma, which is this, which will be the usual Wilson loop, right? And then I have in the direction of tau, but keeping zeta and sigma constant. And in direction of zeta, keeping tau and sigma constant. The funny thing is that the one in the sigma direction is invariant under the charge. It's quite simple. It doesn't even depend upon the constraint, nothing. But the other ones have this transformation. Again, they pick up the same phases, you see, the same nature, but these S, R, and SL are different, and they are different for tau and zeta, okay? But you have two terms. One T appears on the right, and here on the left, okay? But they are like primary fields, you see, because the transformation is linear on them. So when you exponentiate things, you are going to get a group element multiplying it, okay? So, without the trace. It doesn't have to be closed. No, because these things don't match. Because if you take, well, this guy is invariant. Without, I mean, it's invariant even without closing the loop. It's invariant because A sigma is invariant. A sigma is invariant under these global transformations. So if you integrate up to some point in the loop, that Wilson line is invariant without the trace. No, they are not, and the reason is the following. Take this guy, integrate the, let's say, over tau. So you start here, go around the surface and come back. That's a closed loop. The point is, at the initial point, these S have one value, but at the end point, they have a different ones, because they are integrated, you see? So what will come at the beginning and at the end is not the same. They are not invariant. Yeah, they transform, yeah. They transform. That's maybe an example of some, yes, closed loop. That's an example of a gauge invariant quantity which is not invariant under this thing. It might be that in some cases, some field configuration, because this depends upon the field configurations, you see. But in general, no. And that's because it's integrated. This phase gets integrated. So you start with one value at the initial point, and then you have to integrate it all over there, and then it ends up with some value which is not the same. So when you take the trace, you don't cancel. The what? The? No. It's this. These things, they are integrated. Fine. This, take this thing. Is integrated over the volume. The point is that I don't have enough time, but it's this. Suppose you take a point inside this volume, right? So then this thing, it's integrated over the surface, up to the surface where the point is. And then is integrated over the loops up to the loop that passed through it. And then is integrated on the loop that passed through it up to the point where it is. You see? So this quantity here, it's open. It's not integrated on a closed volume. You see? Sorry? Yeah, no. Here, the omega is integrated up to, from here to the original point, up to some point inside the volume, along the tau direction, right? But, so that S there is this. I mean, the point is here. The loop, the omega tau, let's say, is there. So that's the Wilson line. So you have to integrate up to the surface. So you integrate on the volume inside the surface where that final point is. Sorry? Then you integrate. Then you have to integrate up to the final one, and when you go back, you integrate backwards in the volume. No, that has the same nature. SR and SL, they are all built like this. You see? You integrate, if it's sitting on a surface there, then you integrate up to that surface, and then it lies on some loop here that scan the surface. So you integrate over all loops that go there. So you integrate to a part of that surface. And then you integrate up to that loop there. So if you close the loop, so I go here and go back, I'll have to integrate over the volume up to the border and then backwards to the original point. But that's not the same as the initial value of the thing. That's why the trace may not be gauge invariant under the trace. Okay, that's it. That's how this Wilson line transforms. If you take a different direction, so it'll be a combination of all these three directions. So we didn't do this calculation, right? So now is the other symmetry I want to talk about, okay? Is the symmetry of the integral equations. That's quicker. I hope I will not be over time. Is this. So now is a different game, okay? What I do is this. I take this loop space, the maps from the circle S1 to the space-time with the North Pole going to this fixed point. So it's a base loop space. That's the usual loop space that people talk about, is the S1 to M, even though we are using here generalized loop space, you see. Now you take a one-form connection on this loop space, okay? I'll show you, I can show you how you can construct some of these from local fields, but they don't have to be constructed from local fields necessarily. And then I define two holonomies with the same connection. One multiply from the right and one multiply from the left with a difference in sign. But the boundary condition is 1. So the reference point, both are 1. What happens is that one is the inverse of the other. So G hat and G tilde, one is the inverse of it. It's quite simple. For instance, if you take the product from G hat from the left and use the two equations, you get 0. But if this means it's a constant. But this is the value of the reference point, but the value of the reference point is unit. So G hat, G tilde is the identity. Okay? And if you take the other way around, it's a bit more involved. You don't get 0, but you get a commutator. But then you write this connection in terms of a prime connection like this. Multiplying by J hat, J tilde, and J hat. And then you get 0 for the same reason. 1 is the identity. So it's a left and right identity, right? The same thing, that's an important thing. How do you compose these holonomies, right? So given two connections, A1 and A2, you construct the J1 hat and J2 hat. Now forget about the J tilde, right? Because it's the inverse of this. And multiply them and calculate the derivative with respect to tau. You get this. is the same thing multiplied by that thing. So I call A3 that thing. So that's how they connect the one forms compose. You see, you take the A2, which is on the right, all right? You add up A1 conjugate by the holonomy of A2. And the J3, which I define by the product of the two, it satisfies that equation that comes from there. So if I have two holonomies, I construct a third one by the pointwise product of them, and the connections compose like that. So that's the structure of the group, right? One point to be clear now is not, even though my group elements are holonomies of connections, my group is not the holonomy group discussed in the literature. Because the holonomy group in the literature is the following. You take a fixed connection, you fix the connection, and take two loops. And you compose, then you calculate the holonomy in one, and the holonomy in the other, and you compose them by composing the loops. Here, I fix the loop and take two connections and compose them. It's totally different from the usual holonomy group. The holonomy group becomes abelian quite easily, you see, but this one don't. Okay. So it's associative because this is the matrix product, because I need a matrix representation to define these holonomies, right? And the composition of the connection is associative too, right? It's not difficult to get that. And the identity is the holonomy of the zero connection, right? Is this one. And you can check that indeed it is identity, right? So then I construct on this loop space, right? I mean, the connections are in LU1, but the holonomies, they are loops in LU1, right? So these are points in L2. So I define on every point of L2 an infinite dimensional group. And the composition is pointwise on the loop space, right? And then the elements are holonomies of connections in L1, but the group elements are in L2. I define on points of L2. And the composition is pointwise, as I said. It's not the holonomy group, as I said. Now I can do what I did at the beginning. This is a holonomy on L2, so it's a holonomy on a surface, right? Because the map of S2 to M. So it's defined on a surface in space-time. I can do the no-abelian Stokes theorems for these group elements. And I can write the same group element on the volume inside the surface. So I can write the group elements in two ways, either defined on the surface or on the volume, which border is that surface, using the no-abelian Stokes theorems I explained to you at the beginning. And then the symmetries are quite simple. I have my integral equation, the integral Young-Mills equation, right? So you multiply from the left, right? Here is integrate on the border, so you multiply with the group element, calculate on the border. But it's equal to the element calculating the volume, so you multiply from the left. Since this was equal to this, multiply both, they are equal, you see? And the same from the right. So I have a chiral, let's say, symmetry group on this loop space, which is a symmetry of the Young-Mills equations. Now, this group should act on the space of solutions of Young-Mills, okay? And in fact, it's easy. Take the vacuum solution. So this is one, that is one. And now you take the connection for a monopole, or an instanton, whatever you want, and calculate the holonomy. That's the group element. So you multiply it by 1, you get the integral equation evaluate on the monopole, right? Okay, this you can do if you know the solution. The question, how do you do that without knowing the solution, right? I'll comment more about this in a moment. Look, this one is not a symmetry of the Lagrange or the Hamiltonian. So it changes the energy and can take trivial configurations to non-trivial ones, okay? And as I said, probably is not a Lie group. The reason why we suspect it's not a Lie group is the following. If you try to look at the identity and see all possible directions where you can construct the group elements, the dimension of the space of elements is infinite at the identity and every other point. But the infinity is different from point to point. So it's like the orbifold, right? But the orbifold is finite dimensional because it has one dimension here, another one there, and this seems to be like this. It's infinity in every point, but the infinity is different. We haven't yet catch that. There is another paper to come out in, I hope, in 2 weeks, where we do all these things for 2+1 Young-Mills, right? Things are simpler there, and this group is simpler there. So I think we should start from that group in 2+1 to study the structure of this group, okay? But all these things apply to 2+1 Young-Mills also. But as I said, if it's not a Lie group, that's one of the assumptions of the Coleman-Mandula no-go theorem. So you might circumvent Coleman-Mandula in a way different from supersymmetry. So what that means? It means that these transformations may mix internal and external transformations in a non-trivial way. And that's what you need to have non-perturbative methods in these theories, you see, like in Sine-Gordon. Okay? But that's a long and difficult problem for the students to solve, okay? But the point is, if you, as I said, is a symmetry of the integral equation, but it's a symmetry of the flat connection. The reason is simple, because, as I said, the V comes from these, and you can think of A, the flat connection, as like some sort of exterior derivative of that holonomy, right? So, since that's path independent, this is flat, and that's the Lax equation for Young-Mills, right? And then, if you make those transformations on V, you get a gauge transformation of the connection on loop space. Or you get intertwined gauge transformations when from the right, but from the left is this thing. Okay, so that's the generalization to Young-Mills of the hidden symmetries of Sine-Gordon. Remember, I told you that the usual gauge transformation are the hidden symmetry of the Sine-Gordon. They're not symmetries of the equations of motion, but they are symmetries of the thing. So here is the same. This is not a symmetry of Young-Mills equation, the local ones, the differential equation. They're not symmetries. They're symmetries of the integral equations, right? So they're symmetries of the flat connection. So these are the hidden symmetries of things. So this group here should play in Young-Mills the role played by Kac-Mood group in integrable field theories, right? The problem is, I run out of time, but let me explain one more thing. People familiar with integrable field theories, classical, don't have to consider the quantum case. The inverse scattering method works because there is what is called the Riemann-Hilbert problem. It has two versions. There's the complex analysis version, which is a series of positive powers of a complex variable is equal to a series of the same variable but negative powers. So you have a sum of negative powers of a variable equal to a sum of positive powers. That's the complex analysis version of the Riemann-Hilbert problem. There is an algebraic version, which is called the dressing transformation. And these are the transformations that allow you to construct solutions without knowing them. The soliton solutions of Sine-Gordon are constructed that way. So, if you want to construct solutions of Young-Mills, you have to solve this problem. What's the equivalent of the Hilbert problem here? Okay, then maybe the Atiyah, Drinfeld, and Hitch-Miami method can be phrased with this group. Okay, or the NUM equation for the monopoles maybe can be phrased with this group. Okay, but that's a difficult thing. So I'm finishing. The comments are, the integral equation is a powerful thing to study Young-Mills, classical Young-Mills at least. The truly invasive conserved quantities, oh, that's the thing. They could not be constructed using the local Young-Mills equation. You need the integral equations. And that solved a long-standing problem in classical Young-Mills. And I have these two types of symmetries. And so it has this exact integrability with R matrix, Scalian relation, involution of charge, and so on, as I showed you. And then there is this group. But the thing is this last thing, the hadrons. Go to QCD. These charges are gauge invariant. In principle, they're not confined. So, in principle, the hadrons could carry these charges. We don't know how to answer this question in 4 dimensions. So there is another paper come out in about 2 weeks too, okay, where we went back to 1 plus 1, okay, and did this thing in 1 plus 1. It simplifies a lot. In fact, there is no infinite number of charges. There is just one charge, okay. And then, but we have a charge, okay. So we went to the LATS gauge theories in 1 plus 1 and calculate the expectation value of these charges in the hadrons, or whatever you can call hadrons in 1 plus 1, right? And the quarks. The quarks don't carry the charge, but the mesons and baryons do carry. It will come out in about 2 weeks, 3 weeks, let's say. It's another group that involves my PhD student, but an expert in lattice gauge theories to do that. So the idea is to do the same thing in maybe 2 plus 1 lattice gauge theory first, and then 3 plus 1, I don't know, and see if the hadrons carry these charges. But I want to call your attention. These charges will not restrict the angular dependence of oh my God, cross sections. If you calculate a scattering and calculate the cross section, I don't expect these charges to restrict the angular dependence of the cross sections because they're internal charges. The most they can do is to impose selection rules. So one way of looking for these charges is go to the particle data group and see a process that is suppressed without any reason. Okay? Without any charge that you know that's suppressing that element. That's the way to do it, maybe. How to start. Okay? Okay, that's it. Thank you.
Thank you, Luis, for the nice talk. So maybe 1 or 2 questions?
Can you generate new classical solutions?
Sorry?
Can you generate new solutions of the classical equations of motion from old
Not
ones?
yet, because of this problem, the Hilbert problem. Because, you know, if you go, it's quite easy to see. If you go to the sine Gordon, I wrote in 0 and 1, let's collide in light cone coordinates. So that thing has a d minus phi t3 plus something, and here has a d plus phi t3 and so on. So these guys, you can grade the Kac-Mood algebra, and they live between 1, 0, and -1 grades, the connection, A mu. the grade of Kac-Mood minus 1, 0, and 1. This guy has grade 0, this guy has plus 1, 0, and minus 1. Okay? So when you make a gauge transformation, minus 1, the transformed gauge transformation will transform a mu in all directions of the Kac-Mood algebra. Then you cannot reconstruct the phi field, right? But that's what you want. You want to reconstruct the phi field. Because if you start with a vacuum solution, you do this gauge transformation, you get a non-trivial one. But it's scattered in all directions, so you cannot reconstruct the phi field. So, but the dressing is this. You make a gauge transformation with element G+, which involves only positive grades or 0, and a gauge transformation with a G-, which involves only negative grades and 0. And you can, quite easy, I don't have time to explain, but we can discuss this, but they do the same gauge transformations. They're different group elements, but do the same gauge transformations. And then one, the G+, take this guy that is from minus 1 to and goes to infinite. And this guy takes that one and takes to minus infinite. But they are equal, so then it's bound to be there. And then you get this connection when you have two gauge transformations doing the same thing, you can reconstruct the phi field. We don't know how to do that here. You see, I don't even have a grade, and I don't think it will be a grading, it will be something else. That's, guys, this is a completely new problem, and I expect I live to see the solution of it, and I don't expect I will find the solution. I'm too old already, but that's for mathematicians. I have discussed already with mathematicians, they have no idea, you see. It's a new thing, I mean, it's completely new. And might not do what we want, right? You waste your time. I hope not.
Okay, so if there are no more questions, we thank Luis again.